today. An exciting day. All right, so here we go. I need a calculator. Find components for this vector. Okay. Look at this nice clean board. Isn't this awesome? I've saved this for just this period. Just for you. All right, so when we say find the components, what we mean is find x, comma, y. Those are the components. In terms of what we talked about last time, that's R and that's theta. These are the polar coordinates right here. The polar distance and the angle and standard position. So how do we find x and y? If you can't do this, I will personally smack you on Friday when we take this quiz. How do we find components? X equals 14 cosine 237 and y equals 14 sine 237. That is all there is to it. Now, of course, if you're going to type this in on your trusty calculator, you have to make sure that you are in degree mode, right? Because otherwise it's not going to come out right. So, x equals 14 cosine 237, so negative 7.62, and 14 sine 237, negative 11.74. Done. Next problem. We have 3 points, C, H, and S, and I'm not plotting them on the coordinate plane because it really doesn't matter. If that bothers you, go ahead and plot them in the coordinate plane. These are points. And my job is to find angle C. Now, I talked about this with one of the classes last time. Was it you guys or the other group? It must have been the other group. Okay. We've got options. We always have options. Can you think of an option to find angle C? So find the length of each side, the magnitude of each side, the length of each side, and then you would have all 3 sides of the triangle. So you could use the law of cosines to find the angle, right? That will work. Now, do you understand it will work, but it will be messy? Because what's going to happen when I start finding the lengths of these sides? They're all going to be radicals, and some of that's going to get squared out in the law of cosines, but some of it's not, and that's okay. If you want to do the problem that way, it will 100% work every time. Okay? I'm going to give you another option. I want you to think about this angle right here, and from geometry we know that an angle is the union of 2 rays with a common endpoint. So in other words, angle C is right here, right? Yeah. What are the coordinates of vector CS? This vector right here. What are the coordinates of that vector? Negative 2, what? 9. Negative 2, 9. And what are the coordinates of CH? Yep. Now, it is extremely important that if you're going to do the problem this way and you're finding angle C, that the vectors you use are CH and CS. Does that make sense to you? Those are the 2 vectors that make angle C. Now, I can find the angle between 2 vectors using the dot product. Do you remember that? What is the dot product of these 2 vectors? Dot product, x times x and y times y. So I think the dot product is 68. Yep, nod or something. But the dot product is also the magnitude of the first vector, which would be the square root of 4 plus 81, so root 85, times the magnitude of the second vector, which would be, oh my gosh, is that also root 85? Well, that's remarkable. Times the cosine of the angle between them. That's random luck. I couldn't do that again if I tried. Okay, random. Now I can set those equal to each other. So basically 68 equals 85 cosine C. So cosine C equals 68 85ths. And how do I find C? That's not S, that's C. How do I find angle C? Second cosine, inverse cosine, 68. I got 36.87. So again, it will absolutely work with the law of cosines. It will also work using the dot product. Whatever you feel is, handiest for you. All right, any question about that? What vectors would I use if I wanted angle H? HC and HS. So if you use this method, it's really important that you start out with the right vectors. So be careful. Pay attention to the angle you're after. All right, find the magnitude and direction angle for this. Now we're not confused by the I and the J because we just remember that I and J are the horizontal and vertical standard unit vectors. So this just means one step in the X direction and negative 4 steps in the Y direction, right? So this guy looks like this. These are the rectangular coordinates, and I need the polar coordinates. I need this, which is R, and this, which is theta. So that's easy. How do I find R? Pythagorean theorem. So my magnitude, the question says, what's the magnitude? So I'm going to say the magnitude is root 17. And the direction angle will be this right here. But I'm not going to be able to find that right away. So I'm going to go to my calculator and I'm going to find this one. So I will second tangent 4, or 1, 4. And this is 75 point something. So I'll just subtract that from 360. And it's 284.04 degrees. If the directions happen to say, there's no directions here. If they happen to say answer in radians, nothing would change. You would just have to be in radian mode. And you would subtract your reference angle from 2 pi if you were in radians. You just have to follow directions. If there are any. Well, I've already got the negative because I'm in this quadrant. I just need to know how big this is. And if you put in negative, you get the same angle. It's just negative. You never need the negative if your job is finding a reference angle. If you want the reference angle, you don't need the negative. You learn it in the right quadrant. All right, number 4. This is one of the problems that bothered us in our homework, or something like it, bothered you in your homework. Find the actual speed and direction of a plane traveling 400 miles an hour on a course of this, and the wind is blowing this. Now let's understand that the actual speed and direction of the plane is a combination of his initial speed and direction and the wind, right? In other words, what you're looking for is the resultant of those two vectors. Resultant means we're going to add them together. So we're going to find the components of the plane. Now, what makes this tricky is, components is easy. R cosine theta, right? The problem is, you got to get the right theta. If this plane is on a course of north 17 degrees east, this is the plane right here. North 17 degrees to the east. Theta is not 17. This is theta. Does that make sense to you? Because when we are doing math, we use angles in standard position. So how big is the theta for this guy? 73 degrees. So your components for the plane are 400 cosine 73 and 400 sine 73. Now we don't need to type those in just yet. Those are the components for the airplane. Now, the wind is on a course of 160. Now be careful, a course of 160 means this, doesn't it? Would you agree? Theta is not 160. Theta is this. Theta is your angle in standard position. Navigational angles must be changed into standard position before you do this problem. Okay? So let's see, how big is that angle?
290.
Somebody said 290? How did we get 290? Well, I don't know, there's lots of ways to think about it. Would you agree this little guy right here is 70? So that's everything except 70, so 290. So the wind has components. X equals, how fast is it? 72 cosine, what did we say that was, 290? And 72 sine 290. Is everybody with me so far? Okay, big red flag, if it's a navigational problem, make sure you convert your angle to standard position. Okay, now the resultant. The resultant is the sum of these two. So I'm just going to add my x's together. So 400 cosine 73, close parentheses, plus 72 cosine 290. I got 141.57. For x, tell me if you get that. I'd like somebody else besides me to be typing this in. $314.86. Are we on the same page? Okay, now what have I just found? What are these? These are the components of the resultant vector. That is not what the question asked me for, right? So I'm going to go ahead and take a look at these components. It's over 141 and up 314. So it would look like this if I drew it. Agreed? the magnitude is r. It's the hypotenuse. So how am I going to find the speed of this airplane? The speed is the magnitude. How am I going to find it? Just going to do the Pythagorean theorem, right? So 141.57 squared plus 314.86 squared, square rooting it. I think this guy's going 345 miles an hour. So his actual speed is 345.22 miles per hour. Now, what is his actual direction? Well, this would be his direction, because direction is measured from due north. So I'll find this one, subtract it from 90, and that will be my direction. You see? All right, so here we go. Second tangent, 314.86 divided by 141.57. I got 65.79, but I don't care. I'm going to subtract it from 90. So my course is 24.21 degrees. So remember, this was the original airplane right here. So that was 17 degrees. Well, now he's pushed down to 24 degrees. Does that make sense since the wind is blowing this way? Sure, it's going to push him down. Tangent is this number over this number. Opposite over adjacent. All right, number 5. Last one. Find the work done by a force of 48 pounds acting in the direction 2-1 and moving an object 4 feet to a point in the first quadrant along the line y equals 4x. Work. How do I find work? What's work? Work is force times distance times cosine of angle between. Okay? So, 2 of those things we know. We know the force is 48 and we know the distance is 4. So this is done. Now, let's look at what's happening here. We have the line y equals 4x. I'm just going to go ahead and put in, there's the line y equals 4x. And then we have the direction 2,1. So here's the direction right here. So everybody got that? The direction is over 2 up 1. So that's here. The line is y equals 4x, that's there. And this would be the angle in between them, right? Could we find this angle? We could go to our calculators, keeping in mind that the big purple triangle is over 1 up, over 1 up 4. So that big purple angle would be inverse tangent 4. So 75.96 degrees. Would you agree with that? Can we find the little orange angle right here? that's over, was it over, yeah, over 2 up 1. Right here. So what would that orange angle be? Inverse tangent 1/2. I got 26.57. So what's the angle in between them? Whatever those are subtracted, right? 49.39. Cosine 49.39. So 48 times 4 times cosine 49.39. Did you get 124.97? We got some round up in there, but it's okay, there's a lot going on. The unit on that 124.97 would be foot-pounds, because we have a force with feet moving, excuse me, a force with pounds moving an object in feet. All right? Okay. That's your quiz next time I see you, which is Friday. If by chance you won't be here Friday. No, don't just point at him. You're going with me. So, if you're not going to be here on Friday, then you know the drill. It's got to be taken on Monday morning.
Monday morning, right after spring.
No. Take it tomorrow.
So, Monday morning. Wake up at 2. Bring you a treat.
Will we get bonus?
All right. All right, let's finish up our notes. We have a little bit more to do in 6-4. So get your notes out. Up to you. Notes. We gotta get through at least 2 more chapters first. You gotta do that. Alright, so here we go. Find 4 coordinates for the following. Alright, well that's easy. The point that I've been given is 1, 2. 1, 2. And I need to find the polar coordinates basically, I need to find magnitude and direction angle, right? In the vocabulary in the first part of the chapter. Now it's called magnitude, or now it's called polar coordinates, R and theta. So R is going to be root 5, right? And theta is going to be the angle whose tangent is 2. But be careful, this time the directions stipulate we are in radians. So I'm going to change my calculator to radians, and then inverse tangent 2. 1.11. All right, now the next one. I want you to pay attention to what's happening in the next one. -1, 5 are my Cartesian coordinates. The magnitude is root 26. And the direction angle would be inverse tangent 5 subtracted from pi. So I got 1.77. Now look at that. I know that's not the answer to the question, but is it okay so far? Does that make sense to you so far? Second tangent 5 gives me this angle right here. Subtract it from pi. That's how I get my direction angle, my theta. Okay. Now, look at the directions though. My theta's okay, but what's wrong? R is supposed to be negative. Now, when you do the problem, R will never turn out negative. R will always be positive in the beginning. You have to artificially make it negative. And we talked about how to do that. If you're going to change the sign on your R, then your angle is going to have to be changed by 180 degrees, but pi radians. So you're going to take that answer right there, and you're going to add pi to it. And it's 4.91. And there is the answer to the question.
So when it asks for the polar coordinates, is it always going to be in radians, or is it only if the...
Only directions say it can be in degrees. It can be in degrees. All right, here we go. The next one. Forget all the other junk. Just handle 1, -3. So 1, -3 looks like this. Its radius is √10. And I'm going to do the reference angle. Second tangent 3. The reference angle is 1.25. So one set of polar coordinates would be √10, comma, 2 pi minus this number, would you agree with me, 5.03? 2 pi minus that would be 1 theta. Now, let's look at the parameters that we've been given. Well, R can be anything, right? So √10 is fine. But what about that angle? It doesn't fit. You have been told you have to be between -3.14 and 3.14, and that angle isn't. That is polar coordinates for that point, but it's not, it doesn't fit what they've set up for us. All right, so let's make some adjustments. This is not going to work, so what do you think will work? Could I say √10 and then -1.25, would that work? Would you agree with that? That'll work? Now, R can be anything. So what if I made R negative? Come back up here to this point I crossed out. If I make my R negative, then I'm going to have 5.03 minus pi, 1.89. Does that fit within my parameters? So look at that for a minute, let that digest. Remember, one of the major points I tried to make last time was that polar coordinates can be named infinitely many ways. And sometimes it just doesn't matter, just name them normally. But if you are given specific ranges for your theta and your R, then you're going to have to manipulate what you got to fit those. Does that make sense? Perfect. All right, one more set. This is all calculator. So use your grapher to match the polar equation with the graph. Okay? So you're going to type in probably the equations one at a time and see what they match. Now, let's talk about how to set it up here. If we are in radians, which we are, and that's fine, in window, make sure you're going from 0 to 2 pi, because in radians, you want to go a revolution, and in degrees, you want to go a revolution. But in radians, it's 0 to 2 pi. Anybody remember what I told you? Wait a minute, I gotta get the polar. So, I'm going from 0 to 2 pi in radians. And what did I tell you about theta step yesterday? 0.1, yep. Let's go with 0.1 if we're in radians. We may have to adjust it. Well, let's start with that. And then your x-min and max, let's just stick with -10 and 10. Let's just stick with the normal window and see what happens. All right, let's put in the first equation there, which is, uh-oh. How do I put a cosecant in? Exactly, so this is gonna be 5 divided by sine theta. Would you agree with me? All right, let's take a graph and see what happens. Whoa, what'd you get? Did you get the horizontal line? Okay, so that one matches up with picture B. All right, let's go to the next one. 4 sine theta. What'd you get for 4 sine theta? Number 32, what'd you get? Yep, you got the circle, didn't you? Remember how if our circle doesn't look real circular, how do we fix that? Zoom, square. All right, 4 cosine 3 theta. 4 cosine 3 theta. Woo! We're going to talk a lot about these in just a couple of minutes. That matches C. Does that match C? And then for sine 3 theta, we know which one it has to be, but let's just graph it just for fun. Now, let's talk about this real quickly. Does it make sense to you that the graphs of 33 and 34 are so similar? I want you to think about the graphs of sine and cosine, guys. Are the graphs of sine and cosine similar? Aren't they exactly the same but shifted? So changing from cosine to sine in these polar equations just shifts your picture, right? Just rotates it. The shape's the same. It just rotates it. All right? If you got issues and can't get it typed in, you're gonna have to come to office hours or find a friend, okay? You gotta be able to type these in on a calculator. Okay. 6-4 is due on Friday.
6:30? Is 6:30 tomorrow?
I think so. Whatever I put in Power School, I fixed it this morning, or whatever I put in schooling. It's in. Okay. Now, guys, listen. There are 4 shapes. You know, okay, if you're flying somewhere, take your little calculator along, and on the airplane, just start playing with these things. You can get all kinds of different shapes, but 4 of them are called the classical curves because they were studied extensively, most extensively, by the ancient Greeks that just spent a lot of time with trigonometry. All right? So the 4 classical curves actually are the one you just graphed. Those last 2 that had the 3 little loopy things on them, that's called a rose. So one of the classical curves is a rose. Now the ones that we looked at have 3 leaves, but a rose can have 4, 5, 6, 7, it can have lots of leaves. And we'll look at some of those. Another one of the classical curves is the lemniscate. Okay, so the rose is one that looks like a flower, right, with petals. A lemniscate is a figure 8 shape. Now that figure 8 can be situated sideways like I drew it. It can be up and down. It can be diagonal. This is one of these really corny Mrs. Ford deals. If you mispronounce this word, you might say lemniscate figure 8. That's how I remember it. Now, please don't call it a lemniscate because it's a lemniscate. But if you pronounce it wrong, lemniscate figure 8. That's how you will remember. Okay, another one is the lima sign. The lima sign has a shape like a lima bean. Lima bean. But it's lima sign. But it has a shape like a lima bean. It does not have to have the interior loop. Some of them don't. We're going to talk about how come they do or don't. Also, they can be pointed any direction. So like this one is on the left. I'm not a very good artist. This one's on the left. It can be dented in at the top or the bottom or sideways. Okay. And then the last classical curve is one of the most interesting, but it's also one of the hardest to graph. It's a spiral.
So basically the graphs on our homework.
Yeah, for some of them, yeah. So these are the classical curves. Okay? So one question at some point in your future might be named the classical curves. Right there they are. There's the names. Now we're going to look at each one carefully and talk about some of its characteristics. So the very first thing that I want you to do right now on your own, I want you to be in radians. I want you to be theta from 0 to 2 pi with a step of 0.1 and negative 10 to 10 for your x's and y, max and min. And I want you to graph these four. 1, A through D, I want you to graph them. And I want you to do a quick little sketch there so that you remember what it looked like. And then I want you to make some general observations so that we can talk about problem 2 without a calculator. Everybody should be typing this in, and everybody should be getting pictures. Yeah, so type in your equation.
It's more like a little. I don't really see the.
Well, then you're doing something wrong.
Yeah.
No, that's gross.
Have you ever seen a Google something?
What's your equation? Type it in. What's your problem? Hit graph. Hit mode. Gotta be in radians. If you're setting theta between 0 and 2 pi, you're doing it in radians. If you're in degrees, do it from 0 to 360. Same picture. Picture will be the same. Are these roses?
Yeah.
Are they all roses? They better be. They're supposed to be.
B is like a it's like a cool rose. It's more like a little. It like keeps going though. Like they can't stop.
Now, we got to make some observations here because Mr. Chevy and I are going to ask you questions about these equations, and you're not gonna have your calculator. You're going to have to know about the equation. So, first of all, the first observation is that every single one of those equations is a number times either cosine or sine, and then something theta, right? That's the style of it. There's no addition, there's no squares, it's 5 cosine 3 theta. That's the shape of a Rose equation. Now, what was different about your A, B, C, and D? Let's talk about it. What did A look like? How many petals did it have? All right, so it had 4 leaves. Can you tell on your graph how long those leaves are? I don't think they're 20. Can you tell about how long they are? There.
2.
Actually, in letter A, they are 3. They should be 3 long. The length of each leaf should be 3. I know it's hard to tell because on that one, I think they're slanted out. You don't have one on the axis. So it's hard to tell. Take my word for it, they're 3. Now, what about B? How many leaves does B have, or how many petals does B have? 8. And how long are they? They're 5. And what about C? How many leaves we have? 3. And they are 4 long. And how about D? You got 5. And they are 2 long. That should be a little tiny one. Is it all squished up in the center? If that happens to you and you want to look at the picture more carefully, remember you can change X and Y. Make them smaller and then we'll play that up a little bit. All right. Tell me some general observations here. What do you notice? Alana?
In the 2 top problems with 1 leaves, the first number is bigger than the second.
Okay, it is down here too.
Well, I mean, in the equation, 3, if 3 is bigger than 2.
Okay. Yeah, that doesn't really, you're right. I mean, it happens to be that, but that really doesn't have the implication in the graph. What?
The number before the sign is how long
So the number out in front of the problem, the number out in front of the equation tells you how long the leaves are. Now stop and pay attention to me. Remember a long time ago when we graphed things like this? What did that number out in front do? Made the curve taller. In a rectangular system, that number makes you taller, right? Elongates it. In a circular system, that number simply makes it go out further, right? That's like the amplitude number. So this is going to give you the length of your leaves, that first number. All right, tell me about the second number. Okay?
When it's an odd number, it has that number of
Exactly.
leaves. When it's even, it has that way.
Exactly. So the coefficient on the data tells you how many leaves you have. If that coefficient happens to be odd, then that's how many leaves you have. But if that coefficient is even, you're going to have twice that many. Without graphing any of these, tell me what happens. Those were all sign problems. What happens if we went back and did the same exercise, but they were cosines? What would happen? Exactly, Mary. You'd have the same exact picture, but it would be rotated, because the only difference between sine and cosine is a shift. In a rectangular system, the shift is horizontal, but in a polar system, it is a rotation. Right? That's it. Okay, so without sketching, tell me what 2A is. It's a rose. First of all, you got it classified. It's a rose, and it has 20 leaves that are 14 long. Now, that's a useful piece of information to know, because if you were going to graph it on your calculator, negative 10 to 10 wouldn't work, right? You'd have to be bigger than that because the leaves were 14 long. All right, tell me about B. 9 leaves, 8 on. It's a rose, and it has 9 leaves, and they are 8 units long. Well, yeah, but yeah, it would be oriented differently than a sine curve would be. All right, everybody good? Okay, that's the rows. We've talked about the rows equation. We know what they look like, and we know what the numbers mean in there. All right, let's do 3. Do the same thing. I want you to graph 3, A, B, C, and D. Either draw a picture or take some notes. So we can discuss what in the heck is going on. Does everybody recognize these guys are not roses? How do I know 3A is not a rose? It's got a plus in it. Roses don't have pluses. Okay, if you want to see something just funky, I accidentally forgot to delete a theta here and press graph that on your calculator. Look at that shape. I told you could get good shapes. It's like an octopus or something. Isn't that weird?
Oh my God. Technically, you're just oh my God. It doesn't work, but it's still going. Why do people keep saying TC? That's what it is.
All right, now, what did you notice about this? It's kind of hard to see, so I think I'm going to have you do a little tracing so that you can tell for sure. But it's kind of hard to see. What did we end up with here? I heard somebody say it's an oval. It's not really an oval. These are all limacons. And they have different degrees of indentation. The last one not only has an indentation, but it also has an interior loop in it. The second to last one, did the second to last one have a very clear indentation for you? Clearer than the other ones, I mean? Now, let's talk about that one first. R equals 3 plus 3 sine theta is a special limacon. It is called a cardioid because it has what shape? It's a heart shape. And that happens, yeah, so next Valentine's Day, be my cardioid. That's what you can say to your girlfriend or boyfriend. Now, that happens because these two numbers are the same. The standard form of a limacon is A plus or minus B sine or cosine. That could be sine or cosine theta. Okay? When A and B have the same absolute value, then you have a cardioid. So, and it'll be a heart shape. You'll see that indentation. Now, depending on positive and negative, sine or cosine, the indentation can be in different places. So I think the one you drew, it was heart-shaped like this. But that heart thing, you could have one that looked like this, or any of the other directions, and that's determined by whether it's add or subtract, and whether it's sine or cosine. But anytime these two numbers match, you're going to have a cardioid. Now look at the equation for D, because it was the only one that had the loop in it, of the ones I had you do. What is different about equation D, Hank?
The second number carries.
Exactly. So when that second number is bigger than the first number, you're going to have an interior loop. Now the loop does not have to be in the same spot, depending on if it's sine or cosine. It can be, on the left side, right side, up or down, whatever. But if the second number is bigger, you're going to have a loop. Okay? So we talked about what happened when the numbers are equal. We get that strong indentation heart shape. And now if this number's bigger, we're going to have a loop somewhere in the picture. Well, what happened to the other two? When the first number was bigger, what happened? We had a flattening of the curve. Flattening. Not a real distinct indentation, just kind of a flattening of the curve. And that's what happens. It's still a limacon. Still a limacon. But not a heart and not a loop. So what are you going to recognize as a characteristic of limacon equation? You're walking down the hall, you find a polar equation. How do you know it's a limacon and not a rose? It has an add or subtract. Okay?
If it's like written 3 sine plus 3, should we just go by the number that's like attached to the like sine and cosine?
What? Tell me again. I couldn't hear you.
So like if it was written like 3 sine plus 3, would we just go by the number that's attached to the
well, 3 sine plus 3 would be the same equation. I would turn it around so it looks like this. This is considered standard form. All right, so redo number 3 using cosine. I don't know if you've done that or not. If you did, what do you think's gonna happen? It just shifted. Same picture, it just shifted. And then we just made observations about the ratio of A and B. You said if B is bigger, we're gonna have a loop. If they're the same, we're gonna have a cardioid. Otherwise, we're gonna have a flattened line of B. All right, we're gonna sketch on the calculator now, okay? Ooh, number 5. What's the problem here? It's R squared. Well, shoot. Do you have the capability of typing in an R squared? You'll have to take the square root of both sides. And when you do that, you're going to have the positive, look for the 2 there. You're going to have the positive square root and the negative square root. So you're going to type those things in. Let's leave everything set up the way we had it. Type it in 2 equations. Second square root, 9 cosine 2 theta. And negative second square root, 9 cosine 2 theta. What'd you get? You got a figure 8. Right, looks like an infinity symbol is sideways. This is an example of a Lundisket equation. This is a Lundisket. What is characteristic about it? What's different about it? It's R squared. If you didn't have this, what does that look like? That would be the equation of a rose. But as soon as you put that in there, now you're going to have a Lundisket. What do you think's going to happen when you change those cosines to sines? It's going to be shifted. It's going to be shifted. All right? One more question before we do the next one. Can you tell how long the leaves are? They're 3. And that makes perfectly good sense. Because if you square root this, doesn't that become a 3? And doesn't the number out in front tell me how long the petals are? Perfectly good sense. All right. Did you graph it? It's not a rose. It's a figure 8.
Oh, there's 2.
All right. For B, would you change the cosine to sine? So second square root, we're going to graph 16 sine 2 theta. And negative square root 16 sine 2 theta. I got a little gap in the middle of mine. Somebody figure out how to close that, I don't know. But is it another Lundisket? Yep. And instead of being sideways, it is on the diagonal. Does that make sense? And you can't really tell from, at least I can't from my picture, how long those leaves are. But I know if this is a 16, I know those leaves are going to be this long. All right? Next time, we'll talk about the spirals. Listen, guys, listen. You are going to need to recognize the classical curves. All right? So please